Okay, so what happens now if we have some data and it's growing and decaying, well, we think it's growing and decaying, and we actually want to fit something to fit in that growth and decay. So maybe you have some bacterial data, maybe you have some, I don't know, atomic data, maybe you have some sort of data from rocks, I don't know, you maybe aging rocks. So we can actually use the least mean squared fit to actually create a relationship or to describe the decay using the equation. So let's take an example. So let's say we have this data here where we have a number of atoms, it's a radioactive decay, and we have time. So we have 120, 130, 170, and 3, oh, so it's 200, sorry. And time we have 61, 25, 7.2, and 2.8. Okay, so this is our number of atoms and t, which we're going to call time. I think we call it little t in the book. So what we want to do is try and get this to fit on this curve, y, a, b to the power of x, which we just described earlier. So maybe we can then fit this into the form of, well, we have n equals a, which was just going to call a our constant, b, which is our t value. We've called it capital T here, and we have some sort of k value here as well. Okay, so we're going to now use this to describe what's going on. So if we were then to rearrange this, so we had this as log n equals k log t plus log a, and here we've used to the base 10. It doesn't really matter what base you use in logs. We're just using log to the base 10. This is an easy way to do this on the computer. Typically, computers prefer log to the base 10, just how they work. So we now have this relationship, which actually is the same as saying y equals mx plus c. So if we were to plot this on these two bars here, we would say log n and log t, we would actually have a straight line, which is pretty handy. But what did we say before? Well, we actually showed that this straight line, we had an equation for that using y equals a plus bx, which was akin to this. It's exactly the same thing. So what we showed is that, well, now we have, well, what we can show is now we have this information, we can then use the same relationship for the least mean squared fit, because effectively our plots are just around this line, and we're trying to find where these fit quite nicely onto the plot. So we can say now, if we make our table of log n and log t, maybe we call this x and we call this y to keep them with our notation as previously. I might just put that there, equals y equals that we did previously. And then we just stick all this in the calculator. We would find that our log t values are 1.792, 1.398, 0.857, and 0.447. Likewise, we'd find our log n values are 2.079, 2.114, 2.230, and 0.447. Okay, so we've worked out our values in terms of logs on this straight line. So, well, we just go back to the equation that we did previously, because if you remember earlier, we did all this kind of s equals sigma, I equals 1, n, y1 minus bx1 minus a, and then we differentiated with respect to a and set that to 0 to minimize it, and we differentiated with respect, oh, I've done it again, that should be d, with respect to b, and then that gave us also a 0 because we're minimizing. And what did we find at the end is we created this set of simultaneous equations, which told us that a n plus b sigma x equals sigma y, and it also told us that a sigma x plus b sigma x squared equals sigma xy. So what we did next is we created this table. We can do exactly the same thing here, where we had x, where we have y, we have xy, and we have x squared. And then we just calculate our values. So we just pick them in. We've already worked them out here. So I think I've actually put these the wrong way around, where this is x and this is y from the example. Anyway, so we stick our values in and we would get 1.729, we get 1.398, 0.857, 0.445, and then we would have 2.079, 2.114, 2.230, and 2.301. XY is 3.726, 2.955, 1.912, 1.029, and our x square values is 3.211, 1.954, 0.735, and we have 0.200. Okay, and then we take our sum values, which means our x here would be 4.495, it would be 8.724, it would be 9.622, and it would be 6.100. Okay, so dead simple. We've just plugged all our numbers in and we've calculated it. We've squared the x, we've got the xy. And just to point out, I've turned this the other way around. So this was our x and this was our y. It's shown in the textbook. So all we need to do now is to put all this into our simultaneous equations. So we can say an, there's how many data? 1, 2, 3, 4, plus b, so sigma x, which is 4.495b, equals sigma y, which is 8.724. Then we can say our next one, which is sigma x, which is 4.495a, plus b sigma x squared, which is 6.100. B equals sigma xy, which is 9.622. Okay, and then we have a set of simultaneous equations. We can work through these, but you know the simultaneous equations, you'll have done it, and you'll find that A therefore equals 2.375, and our B value equals, we solve that, our B value is a negative value, which is minus 0.1729. Okay, so in the form of y equals, we have here our form of y equals a plus bx. A plus bx, our equation now is y equals a 2.375 plus, or minus even, minus 0.1729x. Okay, so great. So we've described the straight line. So we've fitted the data to a straight line and we've described it. Okay, so but now we want to put it back into the original terms. So actually, what was our equation here where we had it as y equals mx plus c? Well, we can see we had this in the terms here. So log n was our y. Oops. Log n was our y. Y equals log n. Our next term was our k log t was our bx. So our k log t was equal to our bx. So that means our k value is our x. So that would be, I've written that badly. So that's our x value, our n value, our b value. So we could say that that would be minus 0.1729, which is our k log 729 log t. Okay, and we have our final, which is our point in which we cross the intercept, which is our log a. So our point here, which is 2.375, which would be our log a. So log a equals 2.375. So all we have to do now is a little bit of tidying up. So first of all, we'll solve for a. So we can say that a equals 10 to the power of 2.375. Therefore, a equals 237.25. And we can actually begin to describe our equation here. We know what our k value is, and because we have our previous equation, which was n equals a t to the k, or we describe that as log n equals k log t plus log a. Well, actually, we can begin to stick all this back in because this just goes to this with our laws of logs. So our answer and our description would be n equals 237.25 t to the minus, and our x value here, which is minus 0.1729. So this is our description of our decay. So what we've done now is we've taken some real numbers, some real decay numbers, and we've fitted a curve to fit to actually what we want to solve. So as you can see, this is quite generic, and potentially you might have we've got a line squared here. We could go to a polynomial. We just need to differentiate the polynomial, which is maybe a little bit more than what you've done already. And we can actually maybe put this into Excel. Excel does do this decay fitting, but I'm not always sure how it works. It might not be perfect. So perhaps if you have some real data in one of your assignments, you might just want to follow this method through, and this will actually help you fit data, or fit real data, real experimental data, to a curve. So you can create a description of multiple sets of data. So previously, last week, we took single data, single variables, as they evolve through time or something like that. And we created these histograms, which helped us describe in pictorial sense, shows how data spread, how data was, where the middle point was, the range of it, what the distribution was like, if it was modal, if it was bimodal. And what we've done in this data set is we've created a straight line. So we've fitted a single descriptor showing how proportional a data is. We've done some fancy division as such, I would guess. And then we've also looked at decays, and these decays, we've now looked at fitting a line or a descriptor, creating an equation to describe how something decays or something grows. So that's been the end of statistics. And next week, we're going to move on to some brief mechanics, and we'll start to build from there.